So are you able to see the screen?
Yes, sir. Yes, sir.
Okay, so actually in the with the introduction of the inductors which I had explained you last time, we went with this equation which we know for the inductors. That is, the voltage across the inductor is related to the current which is flowing into it by this expression, which is L di by dt. So L is the value of the inductance and the I is the current which is flowing into it. So we know that this is the equation which actually governs the current and the voltage across the inductor. So this is basically called as the inductance. And if you look closely into the physics of this part, what is this exactly? It is basically the variation of the flux linkage which is going across this inductance. So if you apply a voltage source, alternating voltage source to the inductance, then what happens is, you will have some fluctuation in the magnetic field, and that will create a flux around this inductance, and the flux which is created across this inductance we denote it by phi. So what happens is the voltage induced in this inductance, which we call as V here, the capital V, which is the voltage induced in this inductance, that is nothing but basically it is basically N d phi by dt. So what this is basically this is the voltage induced in this inductance, and it depends upon the N, which is the number of turns in this inductance. So earlier we have never discussed about it, but N is nothing but it's the number of turns which we have in this inductance times the rate at which the flux around this inductance changes. So this is the rate of change of flux which is there. So what happens is normally what we do is we actually take the derivative of this flux with respect to the time. So it is if we readjust these derivatives with like this, what I am doing is I am taking the derivative with respect to the current now. So if I do this type of adjustment, I think it will not be a problem for you to understand that these di's and this di will cancel out, and ultimately you will reach to that same flux linkage with respect to the time which is given over here. So it's just the adjustment of the derivatives. So once we have this, you can clearly see that this particular term which is over here is basically called as L. So L is nothing but it's the self inductance which we have over here, which is given this side, and what we call L as the self inductance or inductance. So earlier when we were discussing inductance, we were calling it as inductance only, but now we will introduce another term related to it which is called as self inductance. The thing why we are calling it as self inductance will become clear in a second, but now we are calling it as self inductance here. And this particular L, which is denoted by N d phi by di, is the self inductance. Okay, so here now we have this self inductance. So this concept we have already studied, where we have inductance which is connected to the alternating voltage source. But now another situation comes like this. In this particular situation, what experimentalists have seen, that if you have this original circuit which is already given on the left side, this is the original circuit which we already have in the left side, and we have already dealt with it already. Okay, we have already seen so many circuits involving L and R and all these stuffs. But now what they have seen is, if they keep another inductor in close proximity to this inductor, what they have seen is, they have seen some fluctuations in the voltages. So if they apply a voltmeter across this, what they have seen is a deflection in the needle. So they were surprised, like why this is happening, even though these two inductors are not connected by direct electrical lines. If you see, this circuit is this side, and another circuit is this side, but there is no connection in between the two. So they were surprised, like what is the reason why we are getting the fluctuations in the voltage in the voltmeter, even though if these two circuits are not connected to each other. So what they observed is that these flux lines which are actually here, which I have already told you that the flux lines will be created when the current is passed through this inductor. So what happens is, these flux lines which are there, what happens is these flux lines interact with this inductor also. So the basic flux line which is already there, the first one, this is the main flux. So what happens is when the inductor, a current passes through this inductor, we have this main flux, let us say this is phi 1. What happens is this phi 1 actually breaks down into two parts. The first part retains with the first inductor, and the second part actually becomes an interaction between the first inductor and the second inductor. So this part is this part. So basically this part is this part, and this is the flux related to this inductor itself. So the total flux is nothing but this flux plus the interaction between the two inductors, and that happens because of the mutual flux which is coming in between the two. So you can see from the diagram we have this mutual flux which is generated between the two coils, and this flux is related to the original flux that we were already discussing. So what happens now is we will have this secondary voltage ES generated, because what you observed at the output is the deflection in the voltmeter needle. That is nothing but this ES, which is the secondary voltage generated. So this side is called as primary side, and this side is called as the secondary side of the transformer. So we have this architecture which is drawn over here. This is called as transformer. So this particular circuit topology is called as transformer, and what it is doing, it is transforming the voltage from here to this side. It is transforming the voltage from here to this side. So what is the use of this particular circuit? The use of this particular circuit comes in when you charge your mobile devices using your either mobile devices or your laptops. If you use it, you will be using some adapters for that, and that adapter actually has these voltage transformers inside it. What happens is your electronic devices normally work in the range of 5 to 15 volts. So depending upon your device, whether it's a laptop or a desktop or a mobile, so the range of voltage at which these devices will be working, electronic devices will be working, is between 5 and 15 volts. But the supply which is coming to your home is actually 110 volts. So what happens is we need circuits which can actually down the voltage from 110 to these small voltages. So in order to make these voltages go down from 110 to 15 or 5 volt, we need some circuits which can do that. That is making this particular high voltage to the low voltage like 5 and 15 volts. Okay. So these type of circuits which is given over here, this one actually helps us in doing that, and we will see that we will see in a while that this voltage ES is basically nothing but it's it's k times the the voltage VG. So k is less than 1, so it's basically nothing but k times the voltage VG, and k will be less than 1 normally. So if k is less than 1, you can see that the generated voltage at the secondary side will be smaller than the voltage which is over here. And once you get this ES, you can actually use this to charge your mobile devices. So you can, whenever you connect the your charger to the mobile device, is nothing but you are actually connecting a transformer, a small transformer which takes input as 110 volts at your home supply, and it will actually downscale it to the a smaller voltage of 5 volts. If you read that if you read that charger specifications, you will see it is giving as 5 volt and some 2.1 ampere current, or whatever specification it is giving. So what it says is whatever voltage you apply at the input of that charger, you will get output as 5 volts. So that is what this circuit is all about, and the role of transformer is to downscale the voltage which is coming on the from the input side, and here k is less than 1. Yes.
Sir, it shows power like some watts, and so that's the voltage. From that we get the voltage, and
yeah, from there you can get the voltage, and even voltages are also specified there. Okay, like 5 volt output. So that is basically nothing but it's this point from where you will charge your devices. Okay. So
Sir, why,
yes.
sir, why can't we use amplifiers here or the,
See, these voltages which we are dealing with are very high voltages, right? So we cannot use amplifiers here because the electronic devices that we are, having here, like this operational amplifiers, they normally do not operate at this particular voltage. They normally operate at very small voltages of, 5 or 10. And nowadays it's going down also. So right now these amplifiers are operating at 1 volt and less than that. So if you apply such a high voltage to these operational amplifiers, they will burn away, so you cannot use them. Okay, so the only
oh,
solution that is left is to use passive components. So all these components are passive components. They will not, they will have, their limitations. You cannot apply too high voltages. Some inductors will be given that, you cannot, it cannot handle more than that voltage. So in that case you have to come up with different type of, strength based inductors. You have to use heavy inductors to, handle all these high voltages. Okay, so actually if you observe here, all these voltages are very high. So 110 volt is too high, right? So we go for passive components to do that. Okay.
oh,
So now you can see here in this image. Let me remove this. Yes, please. Any question here?
Sir, what is used in wireless charging?
For this one, in wireless charging, uh, maybe I don't know exactly. I don't know the circuit of that, so I have to see. But
Inductor coils.
it is used. Maybe you can check it. I don't know the circuit exactly of what of wireless charging, but it will be used because because somewhere you will be supplying input to that wireless charger, right? So that wireless charger will be
Sir, it's
taking.
used electromagnetic induction.
No, no, but will be applying some supply to it also, right? To operate it, you need a supply for that or not?
yes,
Yes, sir.
So
So
that.
it is showing that it is like based on the principle of magnetic resonance or
Okay.
inductive power transfer.
Okay, okay. That one I don't know. I'm sorry about it, but I guess we'll be having some sort of transformer there also, because you will be, the ultimate aim of the transformer is to supply to your electronic devices, right? And electronic devices will not be operating more than, 5 to 15 volt range. So in order to downscale the voltages, you have to have a transformer. So somewhere it will be used in that also, in the wireless one. How they are doing it, that I don't know. But as the main priority of the transformer is to downscale, so definitely it will be there in some form or the other.
Okay, sir.
So here we have this EP and ES. This is the induced voltage in the primary coil, and this ES is the secondary voltage which is induced in the secondary coil. So we call this as ES. So basically EP we already know, it is nothing but N times you have d phi p by dt, where phi p is the flux linkage related to this particular primary coil, and this is nothing but I told you already that this you can do like this. You can do this adjustment. So this is nothing but it's an inductance L, LDIP by dt. This you already know. So this is also called as self-inductance. Now what happens is, this ES which is generated again in the secondary coil, which without any connections. So this is uh, basically because of this mutual flux which is coming. So that is the main reason why why this secondary voltage is generated. And this is nothing but it's again, let me call this as NP, which is the number of turns in the primary coil. So this is the primary coil, and NP is the number of turns for that. And then we have NS, d phi m by dt. So here you can see NS, this is the number of turns in the secondary coil, which is the which is the which is present in the secondary portion of it. So here the important thing is this K is called as coefficient of coupling, which is defined by phi m by phi p. That is how much mutual flux is actually contributing to this particular coil, which is on the secondary side of the total flux which is flowing, which is phi p. So they want to understand how much fraction of the primary flux is going into the secondary coil. So that is basically called as the coefficient of coupling, which is called as K. So K determines that how much of the primary is going into the secondary one. So it's a fraction which is defining that. Yes.
Sir, this coefficient of coupling is same that we wrote in ES equals to KEP.
No. That one is different. Yeah, this one is this one which you are talking about.
No.
Oh.
Right now, like when you are learning transformer, you said that ES will be like some ratio of EP. So ES will be equal to KEP. So that is also coupling.
Yeah. That one is coming from that. Yeah, that is coming from that. Yeah. So here, what you can do is you can actually you can use this relation to substitute over here. So once you do that, what you will get? It is ns d by dt times k phi p, and you can bring out k outside. So it is k ns d phi p by dt, which is es. And now if you divide the two terms, which is first term is this one, this is the first one, and this is the second one. So if you do that, what you will get?
EP by ES is equal to EP by KNS.
So what you will get is EP. So ES is nothing but KNS d phi by dt, right? And from here, if you take this, last time what I was telling you here, ES is K times this VG. This K is not that K. Please note that. I will explain you what this K is, which is coming now. So this K is nothing but NP by NS. It's not this K. Okay. So if I have this equation here, and if I have this equation, if I divide the two, what I will get? I will get EP by ES equal to NP by KNS. Will I get it or not?
Yes, sir.
So here this K, normally what happens is, I will explain you in the coming slides. This K is, if I take it as 1, if K is taken as 1, then what will happen is your EP over ES is nothing but NP over NS, right? So from here you can easily see that if you want to generate the secondary voltage, it is nothing but it is number of turns in the secondary inductor divided by the number of turns in the primary inductor times EP. So if this EP is basically nothing but this one, the voltage which is across this inductor. So so what happens is, if this EP is 110 volts, you can adjust your inductor turns. Like if you can adjust your inductor turns, in the primary you can keep something, and in the secondary you can keep something, to get the voltage of ES as 5 or 10 volts, whatever you want. So normally these are the parameters NS and NP, which are the inductor turns, which you can adjust to make your inductors having less value of 5 or 10 volts. Okay. So this is the way we generate a downscale voltage of the higher voltage which is given to us based on the number of turns and the number of turns which we have here. Okay. Okay, so the main idea behind the transformers is to downscale the voltages. So in that case, I have given you a brief introduction of that. So let me show you some diagrams here, which are basically giving you different types of couplings. Like you will have K equal to 1 in this case. So here you have this inductor. Another one is this inductor, which is a real inductor shown over here. So what I am trying to show is, like in this particular circuit, the interaction between this inductor and this inductor is only air. So in between that there is only air. But if we try to put some if we try to put some in some if we try to put these two inductors in some medium, so we want to see how much this flux linkage will be, like how much this flux linkage will be between the mutual and the primary coil. So in this particular case, if I instead of putting it in air, if I put it in steel medium, in the steel core, so steel is in between these two, primary and the secondary. So what happens is this steel is giving you a less resistive path compared to air. Compared to air, which we have over here, steel is giving a less resistive path. So what happens is most of the magnetic flux which is generated by this primary coil passes through this a low resistance path and completely goes into the secondary path. You can see it flux linkage could have gone in this path also, from here also it could have gone, but it's not going in this way because this particular steel is giving a less resistive path. So most of the flux which is generated here, actually it is transferred to this side, leading to K equal to 1. So in this case, K, which is the fraction of the flux generated at the secondary side divided by the fraction of the total flux generated at the primary side, its value is 1, and it shows that all the flux generated here in the primary is going to the secondary side. And practically, if you put some other core, like instead of steel core, if you try to put some other material which do not allow too much, which offers actually resistive path to this thing, then and if you still want to have K equal to 1 in that situation, where apart from steel core, if you have some other material which is not allowing all the magnetic field to pass through it, then you can achieve K equal to 1 using this configuration here. So in this configuration, you can see both the coils are on top of each other. In this case, both the coils are on top of each other, and you can see most of the flux which is generated by the first coil is associated with the second coil also, as both of them are on top of each other. So here also you will get K equal to 1. And if you want a value of K less than 1, in that case what you can do is you can actually move these two inductors apart. So if you move these two inductors in from apart, then you will get some sort of this type of situation here which is given, and here you can see the mutual flux which is connecting the two is less than the primary flux which is generated here itself. And we have this inside as a air core. So it's basically a air core which is like there is no connection in between the two. So in air core you will have K less than 1 because we have this flux linkages going on this way. So phi m is always less than the flux linkage that we have for phi p, that this primary coil. Okay, so this is the concept of flux linkage. And now the important thing which comes into play, which I have not explained you, is this particular term which is given over here, this thing. So here if you see, I can write this also as N as d phi m by dip times dip by dt. Why I am writing like this? Because you can see the IP current is only in this branch and there is no current here, right? There is no current here. So what we are writing here, we are writing in the similar format as we have written for this particular case. Same thing I am writing here. Okay. So if I write like this, what happens is this particular term which is over here is not called as L, it is called as M. This is called as mutual inductance. Okay. This is called as mutual inductance because it is coming on here because of the mutual flux which is generated in between the two. So this term is called as mutual flux. That's why we are now calling inductance as self-inductance if it is the flux linkage related to the inductance which is phi p, and we call it as a mutual inductance when we have a mutual flux between the two inductances, which is phi m. Because of that we have m term coming up. So now so now what happens is, if you have a circuit like this, earlier we used to do, what is the equivalent of this L1 and L2? What is the equivalent?
L1 L2 L1 plus L2.
L1 plus L2, right? So earlier we used to do like this, and L1 was the self inductance, L2 is also a self inductance, and both of them were in series. So we used to write like this, but now we will not write like this, because now we will have a mutual inductance which is coming up into play. So by mutual inductance coming up into play means, like for example in this diagram, if you see, we have two inductance connected in series, and we have an iron core which is connecting in between the two. So what happens now, you can see the direction of the flux linkage here. So the direction of the flux linkage is to the right. If you see, the flux is linking in the first one in this direction, and in the second also it is linking in this direction. So both these fluxes are actually aiding, they are supporting each other, both the fluxes are supporting each other. So in this situation, what will happen? In this situation, if I want to calculate the voltage E1 here, what it will be? It will be E1 equal to L di1 by dt. We will have then the mutual inductance M12 di2, sorry, yes, it will be di2 by dt. Why this di2 by dt? In case if you see here, let us switch the concept. Like if I remove this and put the alternating source this side, will you all agree that the whatever story I have told you will be also flipped? Like if you apply a voltage source here and if you remove here, so whatever story which I have told you for this side, it will be flipped to this side. So
Yes.
so this will also have the mutual inductance now, and this mutual inductance will be coming because of the inductance, because of the flux which is generated here, which is the primary flux, and some of that flux will go this side and it will generate a mutual inductance in this also. So similarly, if you do that derivation, you will get this expression. So here you see, this is the primary flux related to the E1 inductor, L1 inductor, and this is the mutual inductance M12 and di2 by dt, because this inductor will be actually creating a flux in this, which is phi m flux in this. So that flux is created due to the I2 factor. So that's why it is like this, and it's a series connection, so I1 is equal to I2. In both the in this series connection we will have I1 is equal to I2, so you can write it at like this, di1 by dt plus M12 di1 by dt. Similarly, if you write E2, what that will be? It will be L2 di2 by dt, its own self inductance plus mutual inductance because of the current flowing in the first inductance here. So this will have a mutual inductance factor with the current flowing in this. This is controlling the mutual inductance for L2. And you know that again I1 is equal to I2, so you can write like this. So, and the total voltage. What is the total voltage? Total voltage across the whole iron core is nothing but it's E1 plus E2. So if you add these all together, what you will get is L1 plus L2 plus 2M12. So 1,2 and 2,1 both of them are same. So mutual inductance of both will be same. So you can write any one of them. So it will add together and this will give you LDI by dt. So what is the equivalent inductance now? The equivalent inductance is L1 plus L2 times 2M12. Will you all agree on this now? So earlier it was L1 plus L2, but now it is 2 times the mutual inductance. And why this is 2? Because the flux that is connecting the series is aiding each other. By aiding means they are actually supporting each other. The flux is not cancelling each other, it is going in the same direction. So that's why you have this plus factor here and you get this 2 times the mutual inductance. Any questions here?
Yes.
Sir,
Yes.
when to include this mutual inductance and when not to?
What's your question? Can you repeat?
Sir, when we should include this mutual inductance?
Mutual inductances are included when these 2 inductors are close to each other. Okay, if the inductors are close to each other, then mutual inductance will definitely be there in that. In case if the inductors are too far from each other, then then there is no point in including them. Definitely there will be some mutual inductance then also, but the value will be very small. So if the 2 inductance are coming close to each other, then the effect of mutual inductance will come. Okay. So in this particular diagram here, you can see it is
Sir, what is the value of mutual inductance in the above, sir?
it will be given to you.
Sir, can't we get that in terms of L1 and L2?
We can get it, but you have to see, you have to go into the details of them. No, it will not be in terms of L1 and L2. It will be in terms of the electrical properties of this inductor, like flux linkage and all that. So you have to see that in the book what that expression is. I forgot it. Okay.
Sir, in 12th we had m equals to k root L1.
What was there?
M equals to k times root L1 L2.
So that one also can be, we can get it by adjustment of these equations. You can work around and see how you get it. Okay. If you adjust these equations where we have this k and all these factors, you can adjust it to get these values out. That is just mathematical way of expressing one quantity over the other. So it's not an issue, big deal. So this is the mutual inductance, and in this particular situation where you have the fluxes going opposite to each other. In the earlier case, if you see, the fluxes were in the same direction, but now in this case the flux in the 2 inductors are going in opposite direction. In this situation what happens is the equivalent resistance that you will get is nothing but L1 plus L2 minus 2M, because now the flux is opposing each other. So in this situation you have minus 2M. So in both these cases you can see that sometimes plus is coming, sometimes minus is coming. So we have to we cannot draw this diagram to tell you that whether flux is opposing or flux is actually supporting the two. So in order to avoid this drawing of these complex circuits the way it is drawn over here, because it requires the diagram we have to draw, it is very we have to be detailed in this in order to show you that by showing these diagrams of the fluxes, if they are aiding, then you can easily write. But it's too tedious to draw all these diagrams with the details every time. So in order to avoid this situation of drawing these complex diagrams always, what we normally do is we actually use dot convention. So if you use this dot convention, then you can then you can easily understand that whether the mutual inductance will be positive or whether it will be negative. So by saying dot convention means if you have a circuit like this, and if I apply a dot here and if I apply a dot here, so the terminology to say whether the mutual inductance in this case is positive or negative, the convention that we will be using here is like, for example, will be detailed now. So if you have a current I which is going like this in this particular coil, and if the current I secondary is going in this particular coil which is on the right side, so the convention is that if the current is flowing into the dot, and if the current flowing in the other part in the other secondary side is also flowing into the dot, then what we take is we take M as positive. if the current is flowing into the dot here, and if the current is flowing into the dot here, in both the cases we will be taking it as positive. And in the other part, if the current is flowing outside the dots, in both the cases, if the current is flowing outside the dot, in that case we will actually use M as negative. So let me draw all the possible combinations to avoid these confusion. So here what you can see is you can understand the concept in this way. Like for example, you are at this point, you are sitting at this point and you are actually watching the dot from this side, and similarly you are sitting at this point and you are watching the dot from this side. So if you are watching the dot from this side, current is entering into this or not, in the dot. So it's like, it is like, you can say it's a wall or a gate, or a gate or something like that. So when you are sitting here and if you are watching the person, you can say that IP is a person. So if the person is moving into the dot, it is entering into the gate or not, right or not? So it is entering into the gate, so that means in this particular side it is entering into the gate. How about this? It is entering into the gate.
Yes, sir.
So in both the cases it is entering into the gate. That means your M is positive here. Mutual inductance is positive. In the second case, let us say if you have something like this, this is the dot here and this is the dot this side, and if I have a current flowing like this, and in the other case the current is flowing like this, in this situation what will be M?
Negative.
So let us say it will be positive because you are sitting here, right? If you are sitting here and you are watching this door, and the person is entering into the door, so this is entering phase, and in this case you are sitting here and you are watching the person entering into this door, and it's entering into this dot. So in both the cases it is entering, right? So in both the cases it is entering, so it is positive here. What about this? If you have this dot and this dot, and if you have current I1 here and then I2 this side, now tell me.
Negative.
Sir, negative.
So it is negative here. What about this? In this case,
Sir, again negative. Negative.
it will be negative here.
Negative.
And in this case,
मतलब लास्ट वाला ये
Negative, sir.
negative?
ये सेम बना
Same, eh? Okay, I made a mistake, I guess. Just a minute.
Sir, can you explain the third case why it is negative?
Third case means this one? This one?
No, sir, beside.
ये वाला?
Yes, sir.
So here you see, if you are at this point, if you are sitting here, right? If you are sitting here and you are watching a person entering into this box, that means it is entering here, right? In this case, you are at this point, you are sitting here, and it is going outside, right? Current is going like this, right? So it's going outside. So one is coming in, another one is going outside. So in that case, M is negative. Okay.
Okay.
So now let us say if you have something like this, it's a 5 Henry inductor, and then you have a 10 Henry inductor, and then you have a 15 Henry inductor, and you have a dot here, a dot this side, and a dot this side. Okay, and this is L1, this is L2, this is L3, and M12 is 2, M23 is 3, M13 is let us say it's 100. Okay, so if this is the case and the current is flowing like this, Can anyone tell me what will be the equivalent inductance of this particular circuit? I will give you 5 minutes to solve.
Sir, is it 28 Henry?
No, it's not 28 Henry. How much?
26.
Very
Is
good.
it 26?
Right, very good, very good. 26. So
Yeah,
let
sir,
us.
26.
So the thing is, if you see here, we have this mutual inductance in between the two, which is M12. Okay. Then we have a mutual inductance between the two, which is M23, and then we have a mutual inductance in between these three, which is M13. Okay. So if we have this, and let us let me put this down. Let us have a voltage is induced here E1, then you have a voltage induced here E2, then you have voltage induced here E3. So will you all agree that total voltage E will be E1 plus E2 plus E3? Right? Right or not?
Yes, sir.
So what is
Yes, sir.
E1? What is E1? E1 will be L1 dI1 by dt, which is its own self inductance, and then we have mutual inductance coming because of this and this. So what will be the mutual inductance value for this and this situation? Will it be positive or negative?
Positive.
It is positive because in both the cases current is actually entering the dot. So that's why you have M12 dI1 by dt. And again you see we have L3 also and L1 also now. So if you consider these two, what is the case, whether M13 will be positive or negative?
Negative.
Negative. Because in one case current is entering the dot and in another case it is leaving the dot. So that's why it will be negative. So this is the first equation. In the second equation, if I want to write, what will that be in the second equation? In the second, let me copy this. So the second equation will be E2 equal to L2 dI1 by dt plus what is the if you recall, M12 and M21 both will be same, like in this particular case, because mutual inductance in between the two is positive. So if you take for this or if you take for this, the polarity will be the same. So it will be M12 dI1 by dt here. And then how about L2 and L3? Will it be positive or negative?
Negative.
It will be negative.
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 M23 dI1 by dt. So it is negative because current is entering here and in this case it is leaving. So that's why the mutual coupling between the two will give you minus value. Similarly E3, it is nothing but it's L3 dI1 by dt plus M13. It will be negative, right?
M13.
Right. Minus M13 dI1 by dt minus M23 dI1 by dt. So if you add all these terms, E1 plus E2 plus E3, then everything will be so it will be E1 plus E2 plus E3 is equal to L equivalent times di by dt, and this L equivalent will be actually nothing but you add up all these terms. So it is L1 plus M12 minus M13 plus L2 plus M12 minus M23 plus L3 minus M13 plus minus M23. So if you calculate all these equations, what you will get is L1 plus L2 plus L3 plus 2M12 minus 2M23 minus 2M13. So if you If you calculate this answer, you will get 26 henries. This is the equivalent inductance. So if you are able to solve this question, means you are comfortable with the dot rule. So what you will get in your exams is, something similar to this. Do not go more into the details of the topics, because this is just a quite a simple introduction to transformers, and try to solve some questions based on these type of activities where you are finding out the inductance, equivalents, and all that.